We are Team Code Warriors and our project title is Road Safety Scanner, and our goal is to calculate distance between off-road obstacles to the lane marking. While driving, we may encounter numerous difficulties. For instance, there could be obstacles like trees or pillars positioned perilously close to the road. Additionally, abandoned or damaged vehicles parked along the roadside impair visibility, increasing the risk of collisions. Moreover, these obstacles can pose a significant challenge when navigating road curves, further reducing visibility. The presence of such close-range obstructions not only contributes to traffic congestion but also heightens the likelihood of road accidents. To enhance road safety, the Road Development Authority will carry out a maintenance process. The first step in this process involves conducting a visual inspection. Inspecting roads manually involves visually assessing the road surface and its quality. However, this method requires a large number of workers and takes a lot of time. It can also be dangerous for the personnel if the road conditions are very bad. The assessment results may be subjective and depend on the experience of the inspector. Our objectives for this project are as follows. Develop a system capable of detecting off-road obstacles such as signal boards, electricity posts, stone pillars, milestones, trees, and other potential hazards. Implement a model that can accurately detect and recognize lane markings on the road. Devise a solution to analyze safety conditions by calculating the distance between the road edge and off-road obstacles. By achieving these objectives, we aim to enhance road safety, prevent accidents caused by obstacles, and provide valuable insights for assessing and improving overall transportation safety. Our final project aims to minimize road accidents and alleviate traffic congestion. By implementing efficient inspection methods, we can reduce the manpower required, expedite the road maintenance process, and ensure passenger safety. Our system is designed with a high-level architecture comprising various components, each employing specific methodologies. Let me explain each component and its methodology in detail. Stereo vision. We utilize stereo vision as it allows for more robust distance calculation. The input video frame consists of left and right frames. Firstly, we split the frame into its left and right components. Next, we rectify both frames to eliminate lens distortion and align objects in the vertical direction using the stereo calibration matrix. Disparity map calculation. With the rectified frames, we calculate the disparity map. This map enables us to accurately determine depth by considering intrinsic parameters such as the distance between the cameras and focal length. Object detection. Using a trained model, we detect objects specifically in the left frame. Once the objects are identified, we compute the distance from the camera to the center of each object, leveraging the disparity map. This process provides us with objects and their corresponding distances from the camera. Lane detection. Another trained model is employed to detect traffic lanes. Prior to feeding the frame into the model, we perform pre-processing steps, such as converting the frame to grayscale, to reduce computational demand. The model outputs lane points located on the lane markings. Similar to object detection, we can calculate the depth for each lane point using the disparity map. Distance calculation. After completing the previous two steps, we have objects and lane points along with their depth information. To determine the distance between the lane points and the objects, we utilize the Euclidean distance calculation. This allows us to accurately measure the proximity between the lane markings and the detected objects. Methodology. In the methodology section, we utilized stereo vision for our system. To validate the ground truth and train our model, we collected data using a stereo camera. The dataset we gathered amounted to approximately 20 gigabytes, with a total duration of 57 minutes. To generate the dataset, we employed the annotation tool called RoboFlow. For object detection, we employed YOLO version 8 and trained it with custom datasets. Initially, we selected a PyTorch model trained with the COCO dataset. With this model, we were able to predict bounding boxes and their corresponding classes. Lane detection. In lane detection algorithms, a combination of computer vision techniques such as edge detection, color filtering, and HUF transforms is commonly employed to identify and track lane markings in a road scene. Initially, we attempted to use a line detection method, but it did not yield the desired accuracy. This approach detected all lines within the region of interest as lanes, including the edges of vehicles. Furthermore, our footage was unstable due to being captured from a motorbike, making it difficult to restrict the ROI. Additionally, line detection algorithms tend to perform poorly on curved lanes. As a result, we made the decision to utilize a neural network-based method and opted for the spatial convolutional neural network. For testing purposes, we used a pre-trained model trained on the TuSimple dataset. Depth estimation. As previously mentioned, utilizing a stereo camera, we can obtain a disparity map which enables us to calculate the depth for each point in the image. Once we have determined the depth of objects and lane marker points, we proceed to calculate the distance between the objects and the lane markers using the Euclidean distance. This distance calculation allows us to quantify the spatial separation between the detected objects and the lane markings. Furthermore, we have the confusion matrix, which provides an overview of the performance of all the trained classes. It helps evaluate how well the model classified each class. These screenshots and matrices offer valuable visual representations and assessments of our system's capabilities and performance. Let's move on to the demonstration. This is the user interface of our application. User needs to select the recorded file and select the frames per second to process. It will upload the video to the server and process it there. You can see the status in real time. After completion of the processing, output video will be displayed here. Let's see the final output from the system. Here you can see, off-road obstacles are being detected and the distance from the lane marking also calculated. In this combined video, you can see all the steps involved in this process from rectification, disparity map calculation, lane detection, object detection, depth estimation, and the final distance measurement. Thank you for watching.